you ever see a headline about some new scientific breakthrough and think, is that for real? Well, turns out you might be right to be skeptical. We're going to break down why a surprisingly huge number of published scientific findings might actually be wrong.
I mean, let's just start with this bombshell of a quote. At least 30% of the time. Just let that sink in for a second. That's a huge margin of error. So how is this even possible in the world of science?
Well, believe it or not, the answer starts in a pretty strange place, an all-you-can-eat pizza joint. Yeah, you heard me. And this one story holds the key to understanding a massive problem that's been hiding in plain sight for years.
So, let's talk about this infamous case out of Cornell University. It's pretty much the perfect real-world example of how science that looks significant on the surface can just go completely off the rails.
Okay, so the setup itself was actually super simple. You've got a research lab, and they're just watching people at a pizza buffet to see what makes them eat more or less. It's a pretty straightforward study, right? But what happened after the study was anything but. Right, so this is where things get really weird. From this one single study, which, by the way, the head researcher himself later called a failure, his lab somehow squeezed out 4 different published papers. And when other investigators took a closer look, they found over 150 errors. Just a total mess.
And you don't even have to take my word for it. The researcher's own words really get to the heart of it. He wrote in a blog post that his main idea, his plan A, just didn't pan out. The data showed nothing. So he told his student to do a deep dive and just find something interesting. And that right there, that's the smoking gun.
So here's the crazy part, side by side. On the one hand, you've got a failed study with null results, and on the other, you have 4 published papers claiming they discovered something. How does that even happen? Well, to get it, we have to look at the statistical tool that's at the center of all this chaos. And that brings us to maybe the most famous and definitely the most misunderstood number in all of science, the p-value.
Okay, here's the textbook definition. It's a bit of a mouthful, I know, but the most important part is that little phrase at the end, assuming there is no real effect. Basically, the p-value imagines a world where your hypothesis is totally wrong and any result you see is just random chance. Let's make that a little more concrete. In a lot of scientific fields, the magic number is 0.05. So a p-value of 0.05 means that if your idea has absolutely zero effect in the real world, you'd still expect to see a result as big as the one you got about 5% of the time, just from pure dumb luck. It's a fluke. And right there, that's the trap. The p-value doesn't answer the one question we all actually care about, which is, okay, I got a significant result. So what are the odds I'm wrong? That number, the real number we're looking for, is called the false discovery rate. So let's actually figure out what that real chance of being wrong looks like. I promise you it's way higher than you think, but the logic behind it is actually pretty simple once you see it laid out. You know what? To make this super easy to get, we're going to use an analogy. Just forget about p-values for a second and think about a simple medical screening test. The math works the exact same way, and it makes the whole problem crystal clear.
All right, let's walk through this together. Imagine we screen 10,000 people for some condition that only 1% of them have. That means 100 people are actually sick. Now, our test has a 5% false positive rate. It messes up 5% of the time for healthy people. That sounds good, but with 9,900 healthy people, that's 495 false alarms. For the 100 people who are actually sick, the test is pretty good. It finds 80 of them. So at the end of the day, 575 people test positive. But look closer. 495 of them are perfectly healthy. They're false alarms.
So, get this. If you're one of those people who gets a positive test result, there is an 86% chance that you are actually healthy. A shocking 86%. That's the false discovery rate. It's so much higher than that 5% error rate you thought you were dealing with. Okay, now let's take that exact same logic and apply it back to science. Let's say we do 1,000 experiments. And let's be generous and say 10% of our ideas are actually brilliant. They're true. That's 100 experiments with a real effect and 900 that are duds. Using our p-value of 0.05, we're going to get 5% of those 900 duds as false positives. That's 45 false alarms. Meanwhile, we'll find 80 of the 100 real effects. So in total, we've got 125 significant findings. And here's the big reveal. Out of those 125 significant findings,
45 of them are just plain wrong. That's a false discovery rate of 36%, not the 5% you might expect from the p-value. It means that when you claim you found something, you're going to be wrong more than a third of the time. And that's before anyone even starts messing with the data. So this high error rate creates this massive incentive for researchers, whether they mean to or not, to kind of game the system. And that brings us right back to the pizza papers and this whole problem of hunting for a significant result. There's actually a name for this practice. It's called p-hacking. It's basically when you torture the data until it confesses. You just keep reanalyzing it, slicing it up in different ways until you get that p-value to dip below 0.05. And this is exactly what happened with the pizza study. When Plan A failed, the lab went on that so-called deep dive. They weren't testing a real hypothesis anymore. They were just fishing around in the data, hoping to snag any random pattern that looked significant enough to publish. You know, the best analogy for this comes from that great webcomic XKC Day. Imagine you want to see if jelly beans cause acne. If you test 20 different colors, just by pure random chance, you're probably going to find one, say the green ones, that seems to have a link. But it's not a discovery, it's just statistical noise. So what do we do with all this? What's the takeaway here? Well, it's not that science is broken. It's that we all need to become much smarter, more skeptical consumers of scientific news. So here's your guide to smart skepticism. First, if you see one single study with a really shocking result, take it with a grain of salt. Wait for other scientists to replicate it. Second, always remember that significant does not mean true. It could still have a 1 in 3 chance of being wrong. Also know that a lot of scientists are pushing for way stricter standards to fix this problem. And finally, here's some simple advice from one expert. Just stop using the word significant. It's more confusing than it's worth.
So I'll just leave you with this thought. The next time you see a headline screaming about a significant link between, I don't know, eating pizza and getting a raise at work, you'll know what might be going on behind the scenes. And the question you should ask isn't just, is it statistically significant, but what's the real chance this is actually true?